This section is about the error bound. It's helping you figure out how bad your estimate is if you when you decide to cut off a Taylor polynomial at a certain spot. Here's a visual of what Maclaurin or Taylor polynomials do for you. A Maclaurin polynomial is just a special name for a Taylor polynomial that's centered at 0. So if you see Maclaurin polynomial, it won't tell you where it's centered, but your center would be 0. Here's a graph of sine of x in the bright blue, and if I approximate it with a linear function, it would be x, which is very good as long as I'm really, really close to 0. If I approximate it with a cubic function, I would get x minus x cubed over 6, and that approximation is better for a little bit further out than the linear function is, and if I use a 5th degree, my approximation is even better. So if I want to be exactly like sine of x, I would need to use more and more terms, and if I want to be perfect, I would have to use infinitely many terms to match the sine of x function. But of course, in the real world, we can't add infinitely many terms. So the real question is, how many terms is good enough? What is my tolerance for error? How much am I willing to be off by? And then how many terms do I need to use in order to be that good? One way to figure that out is to do absolute error. It tells you exactly how bad your estimate is because you are using a kth degree polynomial. You plug in your number, you subtract, and then you find the difference, and that gives you the absolute error. The reason we don't always like to use absolute error is that it requires you first to build your kth degree polynomial and then plug your number in. And if you're going to build it anyway, who cares? Like, that's not really saving you any time. You're going to build it anyway, and then you're going to figure out what your error is. If we do the LaGrange error bound, that says I'm not going to build the polynomial until I figure out how many terms I need to use. And the LaGrange error bound is going to help me figure out how many terms are good enough. Okay. So the promise is that if you use this formula for the Lagrange error, then your actual error, your absolute error, is going to be less than or equal to this estimate. So it's like I'm giving you the worst case scenario, and it's the very worst case. We hope that our error is actually a little bit smaller than that, but it helps us decide how many terms we need, right? If we go worst case scenario. So, for example, if I say I would like to use a 3rd degree polynomial, my error, if I do a 3rd degree polynomial, then this would mean that I'm going to take the 4th derivative and divide by 4 factorial and raise my exponent to the 4th power. It looks very much like a Taylor polynomial formula. The only difference really is that we are going to evaluate this so that our error is as large as possible. So we're going to choose a value for z that makes the estimate as big as possible. We might not, and z has to be between our center and where we're evaluating. It also doesn't have to be exact because we're trying to overestimate our error. So sometimes we're kind of sloppy with that, but I'll show you how we do it. All right. So we're going to use a 6th degree Taylor series centered at 5 to estimate the value of e to the 7th. I don't really want to make a 6th degree Taylor series. I just want to figure out how bad my error is if I did make one. All right. So what I do is I go to that error bound formula and I say I'm going to do a 6th degree error at x equals 7. That requires me to take 7 derivatives of my function. Luckily, my function is f of x equals e to the x, because we're estimating the value of e to the 7th. So our 7th derivative is also going to be e to the x. So for our error bound, we're going to use e to the z, and I'll figure out what z is last. And then we're going to have a 7 factorial in the denominator here, if I can write. And then we're going to have x, which is 7, minus a, which is 5, and that would be raised to the 7th power. All right, now we want e to the z to be as big as possible. And z is going to be, for us, it's going to be between 5 and 7. 5 is where we're centered, 7 is where we're evaluating, so z has to be between 5 and 7. Well, since e to the x is increasing, the largest value e to the z could have would be if z is equal to 7. E to the 5th is smaller than e to the 7th. So my error after for a 6th degree Taylor polynomial is going to be e to the 7th over 7 factorial times 7 minus 5 to the 7th power. We can calculate that on Desmos, so we'll do that. So I grab a calculator and I get that my error is 27.851. Or actually what I get is that my error is less than or equal to 27.851. I would like it to be better than that, but at least I know that if I cut off at a 6th degree Taylor polynomial and I use x equals 7 to evaluate my function, then I'm going to be no worse than off by 27 or 28. Okay. Now let's figure out what the actual error is. Well, the actual error, we have to do all the work of figuring out what our 6th degree series is. So p sub 6. Our first term, our constant term would be e to the 5th. Our linear term would be e to the 5th divided by 1 factorial, and then x minus 5 to the 1 power. And then we'd be at e to the 5th divided by 2 factorial times x minus 5 squared. Oh man, this is a lot of terms. So now I need to keep going because I'm just at the 2nd degree term. So that's going to be e to the 5th divided by 3 factorial, which is 6. And then e to the 5 divided by 24, which is 4 factorial. Then e to the 5th divided by, oops, not 125, 120. And then x minus 5 to the 5th, and we're not there yet, so then we do e to the 5th over 6. I don't know what 6 factorial is, 720, I think. And then x minus 5 to the 6th. We're going to plug 2 into that, and we're going to plug 2 into e to the, so we're going to do e to the 7th minus p sub 6 at 2. No, at 7, sorry. We're plugging 7 is our x coordinate. And I don't know why I put absolute value bars there. So we're going to figure out what our error is then. And I'll show you that work. Oh, I think it's on the next page. All right. So here's that big ugly polynomial. Here's the actual function itself. We plug in 7 to both of those two and we subtract. We get an error that's only 4.972. That's way better than we estimated it using LaGrange error. But boy, was it a lot more work, right? So LaGrange error is, it's promising you that it's no worse than that. It might be quite a bit better, but it's no worse than that. And it certainly is less work than figuring out what the absolute error is. All right. Example 2, what is the Lagrange error for using a fourth degree Taylor series centered at pi to estimate the value of sine of 2? All right, so that means that we're going to find the fourth degree error at 2. Well, if I have sine of x as my function, then the first derivative would be cosine of x. I need to go all the way out to the fifth derivative. But when I take the fourth derivative, I wind up at sine again, and so the fifth derivative would be cosine. So that means our error is going to be cosine of z divided by, we're at a fourth degree, so we're going to divide by 5 factorial. And we're centered at pi, but we're evaluating at 2, so it's going to be 2 minus pi to the 5th power. This is giving us the Lagrange error. And now we want to figure out what value of z to use. And I wouldn't actually think about it too hard. I know that cosine, no matter what z is, cosine of z is going to be between -1 and 1. So let's just use 1 for that and not be too caught up in the nitty-gritty of, do we want to use 1? Do we want to use pi over 2? Not pi over 2. Do we want to use root 2 over 2? Do we need to use root 3 over 2? What are we going to use? Let's just always, when we see sine or cosine, let's say, all right, we're doing Lagrange error anyway. We're trying to estimate the error, and we want to be over abundantly cautious. So let's just use 1 when we see sine and cosine. Right, so now we're going to do 1 over 5 factorial times 2 minus pi to the 5th power, and we're going to evaluate that. And I believe it's here. So here's the Lagrange error, which is 0.016. So we guarantee that your error will be no worse than 0.016. And I actually did the work of figuring out the actual polynomial, and I got that evaluated at 0.893, and we evaluated sine of 2, and so our actual error is 0.015665, which isn't that far off from our Lagrange error in this example. And Lagrange error is a lot easier to find. So that's why we have it. It's just a way of estimating the error, overestimating the error, and we use it because it's easier. We're going to do one more, and we're doing a third degree, so e of 3, and we're going to evaluate it at 2. So we need to figure out our fourth derivative. Well, f is natural log. F prime would be x to the -1. Okay, so we're going to use our fourth derivative, -6z to the -4th. And we're going to be we're going to be dividing by 4 factorial. And we're going to have 2 minus 1 to the 4th power. And now, here's the thing, z is going to be between 1 and 2. And so because we have a negative exponent, I'd like to make that as large as possible. So I'm going to use the 1 to make it as large as possible. So my Lagrange error would be -6 over 4 factorial times 1 to the 4th. I could then figure out a third degree Taylor polynomial and figure out the exact error, but I know that it's going to be no bigger than this. Thank you so much.